So this is problem chapter 23, number 13 on parallel circuits. Again, this one is not in the book, and I added it because I figure it's important to know about parallel circuits and how resistances add in a parallel circuit, and you will see later that they add as reciprocals. Anyway, let's look at the problem here. So it says, for a parallel circuit of three identical light bulbs, each of resistance 4 ohms, and a voltage source that provides 6 volts, compute the total resistance and the total power output. And I'll be looking at the other parts later on. So here's the parallel circuit for the 3 light bulbs. Okay, I'll take the last one away again. A little bit too close. I think I will need a little of space to draw. Okay, and I think the rest I can do by hand. And I guess at some point I decided I wanted to put an ammeter in there as well, so I'll do that. Okay, so this one here is 6 volts. This one is 4 ohms, 4 ohms, and 4 ohms. And the book says, each device connects to the same 2 points A and B of the circuit. The voltage is therefore the same across each device. So imagine that we actually would not have these two here, but just one light bulb. That means across this light bulb we have 6 volts. However, what it is saying is that we have 6 volts across any one of these here, because they're all connected to the same point here. So here is 6 volts, here 6 volts, and here 6 volts, and on the other side it's all 0 volts. So the voltage drop in each one of them is 6 volts. There we go. Then it's saying the current divides among the parallel branches. Ohm's law applies separately to each branch. At this point we actually don't know what the current is, but we can calculate it in just a moment. What we do know is that the current divides among the parallel branches. So that means that a current is flowing in here. So as the total current is flowing through here, part of it will go this way, part of it will go this way, part of it will go this way, and all 3 of these here are added up to be the total current, which is what the next thing says. The total current in the circuit equals the sum of the currents in its parallel branches. The sum equals the current in the battery or other voltage source. It also said in here, I read that a moment ago, Ohm's law applies separately to each branch, and that's how we can determine the individual currents. So I equals V over R, which is individual currents. Remember, 6 volts divided by 4 ohms, so this is just as I used to do before, just this one here applied to just one of them. And that, of course, comes out to 1.5 amps. That means that here 1.5 amps is flowing through this light bulb, 1.5 amps through this, 1.5 amps through this. Incidentally, that was the same current that was flowing through that just simple circuit from a couple of problems ago, and that means that at some point we're going to expect that each of those light bulbs in the parallel circuit has the same brightness as the single one from the simple circuit. Okay, so anyway, so through each one of these here, it's 1.5 amps flowing through. So that means that the total current needs to be added up as the current flowing through the first and the second and the third, which is 1.5 plus 1.5 plus 1.5 in this case. Getting a little off the screen, I guess. And that equals, of course, 4.5 amps. Again, that's what it says. That current divides among the parallel branches. The total current in the circuit equals the sum of the currents in its parallel branches. And that, by the way, is Kirchhoff's junction rule, that the current flowing into a junction, which is this one here, this whole thing here is one junction, is the same as the currents flowing out of the junction. And then actually these three currents are coming back together, flowing, and 1.5 amps at each one coming back together, making a total of 4.5 amps. So the total is 4.5 amps, and actually with that one we can determine right away what the total power is. The power is, of course, current times voltage. The total current is 4.5 amps, and the voltage is given as 6 volts, so the total power is 27 watts. At the same time, we can also determine what the total or equivalent resistance is, okay, which is the total voltage, 6 volts, divided by the total current, 4.5 amps. And you'll be a little surprised because the total resistance comes out to 1.33 repeating ohms. So I'm just going to write down 1.33 ohms so we can see it at least, which is a little surprising because you look at 4, 4, and 4, and how could we possibly come up with 1.33 out of those 4s? Well, one of the things it says here, I haven't read this yet, is as the number of parallel branches is increased, the overall resistance of the circuit is decreased, and that's what we've seen. So we have 4 ohms, and we add 4 ohms and another 4 ohms, and the total resistance is supposed to decrease below 4 ohms, of course. Apparently it is 1.33 right now. Overall resistance is lowered with each added path between any 2 points of the circuit. This means the overall resistance of the circuit is less than the resistance of any of the branches, and that's true. Okay, actually, if you look at the 1.33 ohms, it pretty much looks like 4 ohms divided by the number of branches, which is 3. 4 divided by 3 is 1.33 repeating. I'm not going to write it down as such. This one happens to be a special case for a parallel circuit. Usually resistors, or in this case lamps that have a resistance, are not the same. So the actual formula will look somewhat different than just dividing 4 by 3. But we have answered quite a bit here in this particular part of the problem, and I'll do the resistors later, but let's go to a simulation. And that one is from the last one. I think I'm just gonna see if start this over. There we go. Okay, there's a light bulb, and again it's 4 ohms. Show the value, get another couple. Ohms, show the value, need a battery, and 6 volts for these. I don't think I can turn these here, and alright, I need an ammeter. and I need a bunch of wires. So there's one. Now the first one is gonna go there, and the next one is gonna go here. And I actually already have a closed circuit with the other two being not connected. Actually, that one is my simple circuit. Notice how bright it is. Now I'm going to connect these here. There we go. And there we go. And notice that the brightness actually stayed the same on these. And if I disconnect one of them, like one of them wouldn't work, well, then the other one is still going to work. And that's the nice thing about a parallel circuit. Let me, for example, take this one away. Okay, now, of course, I split the main circuit. So I'll try this again here. Uh-oh. Okay, if I could just move this here carefully away. Just, there we go. Okay, again, it's, there we go. There we go. Now I took this one out of the circuit, but the other one is still working as long as this is connected. So yeah, if I make a cut here in the main circuit, yeah, it wouldn't work. None of them would work. But if I just take one of them out, then the others are still working. Okay, and the third one. There we go. There we go. And they are all of equal brightness. And again, if I just took one of them out, wouldn't matter which one. Carefully move it over there. There we go. I took this one out. The other two are still working in parallel, just equally bright as they had been just a single bulb in a simple circuit. Okay, at this point here, all three of them are in parallel. What we can see here is the 4.5 amps that was calculated times the 6 volts on this one here is, of course, 27 watts. And then if we, for example, measure the voltage on any one of the three lamps, so here we go, 6 volts, 6 volts, all right, 5.99, and 6 volts, or 5.99 rounded to 6 volts. If we determine the current, that may be a little bit tricky. So I'm going to use another ammeter. There we go. And there we go. We can see that it measures, or it'd say that 1.5 amps going to one of the light bulbs, and it would measure the same to the first and the third light bulb. The way I have it wired here, it makes it actually a little bit difficult to measure each individual ones. Oops, that's interesting. Why does it say 3 down here? Ooh, that should be still 4.5. Okay, the simulation for the most part works fine, but here it showed me something strange. That's probably the way I rigged it up, that it doesn't look like it's perfect. Let me actually, I need to fix this here the way I show it, because otherwise this may not, you could always claim that, hey, you know, something weird is going on here. So definitely have to do it. There we go. Here, and you saw these other wires going in there earlier anyway, and then I need to split the junction here and split the junction there and take this out of the way and move this down here maybe, and here. There we go. Put the next one in. Okay, at this point, yeah, this one actually will work. Whoa, I didn't know I could turn that. There we go, and there we go. There's the 1 point.